mass and natural abundance. So natural abundance is basically a percentage saying, hey, we have this much of this isotope and that much of the other isotope. Maybe there's even 3 or 4 isotopes. We're just going to do some simple examples with 2 different isotopes. So what you want to do is you want to take a weighted average between the mass in atomic mass units. So you're just going to take the mass of isotope A, whatever that is, and then times it by the decimalized abundance. Okay, so abundance of A, and then you might have to be careful with like using parentheses on your calculator, and then you want to add to that the mass of isotope B, whatever that might be in AMUs, multiplied by the relative abundance, and you want to have that as a decimalized percent, okay? And that will give you your average, your weighted average atomic mass, okay? So for this one, for example, isotope A, we're going to call tin 112, I don't know, you say 112, however you want to say it. So the mass is 111.90 AMUs. Okay, keep those units in. The abundance is 90.7%. So if I'm going to convert that into a decimalized percentage, it'll be 0.907. Okay, and then I'm going to add to that whatever my second isotope is, which is tin 122. So the actual mass in AMUs of that is 121.90 AMU. And I'm going to multiply it by the decimalized relative abundance, which is 0.093. Okay, I should get a number out of that. It's going to be in AMUs. I've got to be careful with my sig figs, right? So because I am multiplying, I should go to the smallest number of sig figs, which technically is going to be 2, but Alex has asked us to do 3, so I guess we'll do 3. So be careful putting this in your calculator. 111.9 times 0.907, close brackets, plus 121. Oh, my calculator's just not happy with me today. Right, let's try it again. 111.9. I had a sticky button. 0.907. I've had this since like 9th grade, so I haven't even changed the batteries. 0.093 gives me 112.83. I've not rounded that yet. The units are going to be in AMUs. Now, things to check. Is my number in between the 2 isotope masses I was given? Because it certainly shouldn't be less than 111.90, and it certainly shouldn't be more than 121.90. Check, we're in the middle. If you've got like a large difference in relative abundance, like I've got 90% of one and less than 10% of the other, I'm going to expect that weighted average number to be closer to the one that I've got 90+% of. So it should be closer to 111.9 than it is to 121.9, which check 112 is. So the 3 sig figs is just going to be, 8 is 5 or above, so it's going to be rounded up to 113 AMUs. Okay, you want to do another one? Let's do it. Oh, okay. So we've got 2 isotopes of molybdenum. So again, this relative abundance, you've got to convert it to a decimalized percentage. Okay. So it's going to be 91.91 AMUs times 0.46, add 95.90 AMU times 0.54. So my answer is going to come out in AMUs. I've been asked to give it to 2 significant digits, which tracks because my relative abundance is only given to 2 significant digits. So 0.46 plus 95.9 times 0.54. So I'm expecting, we've got kind of similar amounts of both. It should be somewhere sort of mostly in the middle between 91.9 and 95.9, right? So it's going to be about 93.5, 94-ish. Yeah, 94.0646 blah 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 AMU, but of course I've only got to give it to 2 sig figs, which would be this. So 94 AMUs is the solution to that one. Okay, so just remember, if you had like more than 2 different isotopes, you'd have to include each different isotope. There could be 6, right? So just make sure you convert the relative abundance into a decimalized percent and you're golden.